So we've been talking about electron configurations, and now we want to think about how we know what we know, really. And the way that we know what we know is due to photoelectron spectroscopy, which is abbreviated PES. And so again, the photoelectron spectroscopy is going to tell us about, atomic structure, those electron configurations. How do we know that those d orbitals are at higher energy than the s orbitals? It's also going to help us think about ionization energy and then periodic trends. So let's talk a little bit about what PES is. So basically these photoelectron spectrophotometers use high energy radiation, we're talking about UV or X-rays, to eject electrons from an atom. So they're kicking these electrons out of the atom. The PES inputs only one type of radiation, so it's got radiation that's a really specific energy. And because electrons within an atom are in these different energy levels, different electrons require different amounts of energy to be ejected. And so here's really a key thing here. When we're thinking about the energy of those electrons, the electrons that are closer to the nucleus are much harder to remove. There's more attraction between the protons and the electrons when they're really close to the nucleus. Those valence electrons are the easiest ones to remove. And so again, that distance from the nucleus is going to be important when we're looking at these PES. The photoelectron spectrophotometer removes electrons from multiple atoms, and so electrons from all energy levels can be observed and therefore graphed. And so we'll see multiple peaks on our graph, not just one peak. So when we're reading these PES graphs, we want to make sure that we're looking at our labels here. So we have our y-axis and our x-axis, so definitely things you should know. That y-axis is going to be like the signal intensity or number of electrons or relative number of electrons. It's going to tell us how much there is. And then the x-axis is going to tell us either ionization energy or binding energy, or it might have this U here to represent that binding energy. Units are going to be either megajoules per mole, or EV stands for electron volt. So that's another unit that we can use. And the y-axis is going to be labeled backwards. And the reason for that is because we kind of want to think about our 0 point here, our start, as where the nucleus is. Okay, and so that nucleus is going to require the most energy to remove an electron if it was right up there next to the nucleus. And so it's going to go from large here, close to the nucleus, to small out here. And you'll notice also that we have a scale here that is not necessarily consistently numbered, but it is if you realize that it's a log scale, okay? Or there sometimes are those breaks in a line kind of markings along the way. So those are the technical things that are on the graph, but again, let's put it into kind of layman's terms here. Along our y-axis, we're looking at the height of the peak, telling us the relative number of electrons at a specific energy level. The location of the peak is going to tell us how much energy is required to remove that electron. If it's a lot of energy to remove an electron, it's going to be really close to the nucleus, and so that's going to be way over here. Again, we want to think about, and if you want to just label it basically that the nucleus is going to be over here, that's fine. And then these are going to have to be our outermost electrons over here, okay? So here's what some of those graphs would look like. Some of them look nice and clean. The ones that you'll be given will probably look more like this, but they could look also like this. And so we have these different, well, that might not even necessarily be a peak, but we have these different peaks along the way that we would see, okay? So if we take a look at, a couple of elements here, notice how this is labeled here. And this has one peak, and that one peak is one electron high, really. And so this is just representing a hydrogen atom and the one electron for the hydrogen atom. So this would be the 1s1 electron. This next peak then, so now we're up to helium. Notice that it's up here to 2 electrons. So helium has a 1s2 electrons, okay? So the 2 electrons at that 1s energy. If we go ahead and keep comparing our different elements, so notice I'm going from 3 to 4 to 5 to 6 here, we're getting more and more peaks. And so again, that first peak that's closest to the nucleus will always be our 1s peak. In this case, it's 1s2, and our next peak is 2s, and it's only 1 electron tall. When we get up to beryllium, we have 1s2, 2s2, oops. And when we get to boron, we have 1s2, so you're always going to start by labeling those peaks, going from the left to the right, so 1s2, 2s2, and then we have another peak here. This is going to be our 2p1, and then carbon we have 1s2, 2s2, 2p2, and we can keep on going from there. And so eventually, if we get up to something, for example, like potassium, okay, now again, let's think about what we have. We have our 1s peak here with its 2 electrons in it. Okay, we have our next peak being our 2s peak with 2 electrons in it. So they won't always have this perfectly numbered with the electrons over here. So you need to pay attention to the relative size of the peak. And so notice that the size of this peak and the size of this peak here are the same. Okay, and so that's going to be really important to look at that relative size. If we keep going then, next we have 2p6. Then we would have 3s2. Then we would have 3p6, and finally we would have 4s1. And so that's our outermost electron. It is held on with the least amount of energy, and it's going to be considered our valence electron also. So let's take a look at this spectrum. Take a second and think about what you think this element must be. If you said you thought, well, since there's just one peak there and it is two lines high, that this is going to be a 1s2 peak, so this must be helium, you're correct. Okay, let's go ahead and take a look at another one. So, pause the video and try this one. Which element is this? So again, we're going to look at the fact that we have some peaks that are the same exact height here, so that's going to represent the same number of electrons. This first one is going to be the 1s2 peak, then we're going to have 2s2, then we're going to have 2p6, so it's 3 times as high as that other peak, so now it's 6. Then we're going to have 3s2, and then we have 3p, and it's 3 high. And so if I look at my periodic table, what element ends in 3p3? Well, that's going to be phosphorus. Real spectra, again, are going to be a little messier. So this is an example of real spectra. It's often that we don't have exactly pure samples, so they get kind of messy along the way. But know that, this is the same thing that we're doing with actual elements. So this is really the how we know what we know about electron configurations.